August 23, 1943. Yokosuka Naval Arsenal, Kanagawa Prefecture. Chief Engineer Takeshi Yamada stands in the ballistics testing facility, staring at what remains of a Nakajima Sakae engine block. The aluminum casting, designed to power Japan's most feared fighter aircraft, has been split cleanly in half by a single projectile. The 751-grain bullet sits embedded in the concrete wall behind the test stand, barely deformed despite punching through 6 inches of aluminum alloy and steel cylinder walls. Yamada's hands tremble slightly as he lifts the spent cartridge casing. 50 caliber Browning, American engineering at its most brutal. 3,000 miles east, Gunnery Sergeant Frank Morrison climbs into the ball turret of his B-17 over the Solomon Sea, feeding ammunition belts into the twin 50 caliber machine guns that represent America's primary aerial defense. Each linked round carries 13,000 foot-pounds of kinetic energy, more destructive force than 3 45 caliber pistol shots combined. Morrison has no knowledge of the Japanese engineers currently dissecting his ammunition's capabilities, analyzing the metallurgy that makes American air power so devastating. He knows only that when he squeezes those triggers, enemy aircraft disintegrate. 6 months earlier, on Guadalcanal's blood-soaked airstrip, Marine armourers had begun noticing something peculiar about Japanese aircraft that managed to return to their bases after engaging American fighters. The few Zeros that survived combat showed curious damage patterns. Single 50 caliber hits that should have been survivable instead caused catastrophic mechanical failures. Engines that seized completely from projectiles that barely grazed cylinder heads. Fuel systems that erupted into flames from rounds passing inches away from actual tanks. The evidence suggested something beyond simple ballistic impact. But the mechanics lacked the engineering expertise to understand what they were observing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how American ammunition technology came to dominate Pacific skies begins not with military innovation, but with civilian marksmanship and the peculiar demands of killing large animals at extended ranges. John Browning's 50 caliber machine gun, adopted by the United States military in 1933, required ammunition capable of penetrating light armor while maintaining accuracy at ranges exceeding 1,500 yards. The solution emerged from Winchester's ballistics laboratory through systematic metallurgical experimentation that Japanese industry could not replicate. At Yokosuka Naval Arsenal, Chief Engineer Yamada had assembled what remained of the Empire's most experienced ballistics team to conduct the analysis that Admiral Yamamoto himself had ordered. The captured ammunition, recovered from a downed B-17 near Rabaul, represented a technological puzzle that threatened Japan's entire aviation strategy. If American 50 caliber rounds possessed capabilities beyond simple kinetic impact, Japanese aircraft designers needed to understand those properties immediately to develop countermeasures. The testing facility occupied a reinforced concrete bunker originally constructed for evaluating naval artillery shells. Banks of high-speed cameras lined the firing range, capable of capturing projectile impact at frame rates exceeding 10,000 images per second. Precision chronographs measured bullet velocity with accuracy to within 5 feet per second. Yamada had requisitioned 3 complete Nakajima Sakae engines for destructive testing, an extraordinary allocation given the desperate shortage of spare parts throughout the Imperial Navy's air arm. The first engine sat mounted on a massive steel test stand, its 18 cylinders exposed to allow detailed observation of projectile impact effects. Yamada's team had positioned the 50 caliber round to strike the engine block at a 45-degree angle, simulating the deflection shot that American gunners typically achieved during aerial combat. The firing mechanism, salvaged from a captured Browning machine gun, would propel the bullet at its standard combat velocity of 2,800 feet per second. Lieutenant Hiroshi Nakamura, Yokosuka's senior metallurgist, examined the American cartridge with professional admiration mixed with apprehension. The projectile's copper jacket gleamed under the laboratory lights, precisely machined to tolerances that suggested automated manufacturing processes far beyond Japanese capabilities. The bullet's boat-tail design reduced drag for enhanced long-range accuracy. Most significantly, the core appeared to be hardened steel rather than lead, though Nakamura would need to conduct sectioning analysis to confirm the internal composition. "Yamada-san," Nakamura observed, holding the cartridge up to the light. "The jacket thickness appears inconsistent with standard ball ammunition. Notice how the copper extends further toward the base than our own projectile designs. This suggests the Americans are using the jacket for more than just barrel protection." Yamada nodded, his engineering instincts already forming hypotheses about what they might discover. "Proceed with the test firing. We need to document the exact failure mechanism before we can recommend design modifications to the Mitsubishi Engineering Group." The firing control room cleared of non-essential personnel as Nakamura armed the remote. Firing mechanism. Through thick observation windows, the team watched as electromagnetic solenoids aligned the captured Browning barrel with the test engine's cylinder bank. High-speed cameras began their synchronized recording sequences, capturing 30,000 frames per second to document every millisecond of the projectile's impact and the engine block's destruction. The .50 caliber round detonated with a sharp crack that echoed through the reinforced bunker despite heavy soundproofing. For 17 milliseconds, the bullet traveled through air before striking aluminum. What happened next would fundamentally alter Japanese understanding of American ammunition technology and reveal industrial capabilities that the Empire simply could not match. The projectile punched through the Sakae engine's aluminum crankcase as if the metal were paper. But rather than simply penetrating and exiting cleanly, the bullet's hardened steel core began fragmenting in a precisely controlled manner. The copper jacket, designed with specific thickness variations along its length, peeled away in strips that acted as secondary projectiles. Each copper fragment carried sufficient kinetic energy to slash through cylinder walls, sever connecting rods, and shred the delicate aluminum fins that dissipated engine heat. The primary bullet core, still traveling at over 2,000 feet per second after initial impact, struck the engine's crankshaft with catastrophic effect. The hardened steel projectile, now tumbling from its impact with the crankcase, transferred its remaining energy in a devastating lateral blow that sheared the crankshaft completely. The entire engine block flexed visibly under high-speed camera observation as stress waves propagated through the aluminum casting at the speed of sound in metal. Then came the secondary effect that Yamada had feared but not fully anticipated. The bullet's passage through the engine block generated metal fragments traveling at supersonic velocities. These pieces of shattered aluminum, some as small as grains of sand and others as large as coins, became projectiles themselves. They ricocheted through the engine's internal passages, destroying bearings, puncturing oil galleries, and shredding the pursed, delicate valve train that controlled fuel-air mixture. The high-speed cameras captured the entire sequence in excruciating detail. Frame-by-frame analysis revealed that the catastrophic damage occurred within the first 43 milliseconds after impact. A single .50 caliber round had transformed a functioning aircraft engine into 700 pounds of scrap metal in less time than a human eye could blink. Yamada stood in silence, studying the destroyed engine with the methodical attention of an engineer who understood he was observing a problem with no viable solution. The Nakajima Sakae represented the pinnacle of Japanese aviation engine design, incorporating the finest metallurgy and precision manufacturing that the Empire's industrial base could produce. American ammunition had destroyed it effortlessly. "Nakamura-san," Yamada finally spoke, his voice carrying the weight of unwelcome conclusions. "Prepare the second test engine. We need to verify whether this destructive effect is consistent, or whether we witnessed an anomalous result, and retrieve that bullet core from the backstop. I want complete metallurgical analysis of its composition and heat treatment." The young lieutenant moved to comply, but paused at the observation window, staring at the destroyed engine. "Yamada-san, even if we can analyze their metallurgy, we lack the industrial capacity to duplicate their manufacturing processes. The Americans are producing hundreds of thousands of these rounds monthly, while maintaining quality control we cannot match even in small batches." The observation hung in the air like smoke from a funeral pyre. Yamada understood the strategic implications better than most. Japan's war effort depended absolutely on air superiority, yet every Japanese aircraft carried engines vulnerable to ammunition that American bombers and fighters dispensed by the thousands. The mathematics of attrition warfare were unforgiving, and the captured 50 caliber rounds represented just one component of the industrial disparity that would ultimately determine the Pacific conflict's outcome. In Detroit, the engineering decisions that made American ammunition so devastating had emerged from systematic analysis rather than chance innovation. Winchester Repeating Arms Company's ballistics laboratory had spent years perfecting the 50 caliber projectile design through iterative testing that consumed tons of experimental ammunition. The goal was creating a bullet that would reliably penetrate light armor while fragmenting in precisely controlled patterns to maximize internal damage. The solution required understanding metal behavior under extreme stress conditions. Winchester's metallurgists discovered that by varying copper jacket thickness along the bullet's length, they could control exactly how the projectile would fail upon impact. Thicker jacket sections near the base provided structural integrity during the high-stress period of barrel acceleration. Thinner sections near the tip encouraged controlled fragmentation that created secondary damage, far exceeding the primary projectile's penetration. The bullet's hardened steel core represented another level of sophistication that Japanese industry struggled to replicate. American steel mills could produce alloy compositions with precise carbon content and heat treatment that resulted in projectiles maintaining structural integrity through multiple barrier penetrations before finally fragmenting. Japanese steel production, hampered by limited access to alloying elements and less sophisticated heat treatment facilities, could not achieve comparable metallurgical properties. At Lake City Army Ammunition Plant in Missouri, production lines were manufacturing 2.3 million 50 caliber rounds daily by mid-1943. The plant operated with precision tooling that maintained dimensional tolerances measured in 10,000ths of an inch across millions of cartridges. Quality control inspectors pulled random samples from every production lot for ballistic testing that verified each batch met military specifications for velocity, accuracy, and penetration performance. This industrial capacity, multiplied across multiple American ammunition plants, was flooding the Pacific theater with projectiles that Japanese engineers could analyze, but not effectively counter. Every B-17 carried approximately 9,000 rounds of 50 caliber ammunition. Every P-38 fighter carried 1,500 rounds. The sheer volume of American ammunition production meant that even relatively inefficient hit rates still resulted in devastating losses for Japanese aviation. Back at Yokosuka Arsenal, Lieutenant Nakamura completed retrieval of the bullet core from the concrete backstop. The projectile's mushroomed tip and deformed jacket told the story of its passage through aluminum and steel. Under laboratory magnification, Nakamura could see the precise grain structure of American steel, the even distribution of carbon that produced hardness without brittleness, and the sophisticated heat treatment that allowed the core to maintain integrity through multiple high-velocity impacts. Yamada-san, the metallurgical analysis will require several days to complete properly, Nakamura reported. But initial examination suggests they are using a manganese-molybdenum alloy steel with carbon content around 0.4%. The heat treatment appears to be oil-quenching followed by tempering, producing a Rockwell hardness of approximately 55. Yamada absorbed this information with growing pessimism. The alloy composition itself presented challenges that Japanese steel industry could not easily overcome. Molybdenum, critical for achieving the desired hardness properties, was a strategic material that Japan had to import through increasingly precarious supply lines. Manganese reserves throughout the empire were limited and prioritized for naval armor production. Even if Japanese engineers could design equivalent ammunition, their industry lacked raw materials to manufacture it in meaningful quantities. The second test firing proceeded with identical results. The 50 caliber round punched through the Sakae engine block, fragmenting in the same controlled pattern that distributed secondary projectiles throughout the engine's internal structure. The crankshaft sheared cleanly. Cylinder walls cracked from stress waves. The delicate valve train that controlled engine timing was shredded beyond any possibility of repair. Yamada photographed the damage from multiple angles, documenting evidence that would form the basis of his report to Admiral Yamamoto. Each image told the same story. American ammunition technology had achieved a level of sophistication that rendered Japanese aircraft engines critically vulnerable. A single hit from a .50 caliber round would destroy an engine completely, forcing immediate shutdown and probable aircraft loss. The strategic implications extended beyond simple engineering problems. Japanese aircraft designs emphasized lightweight construction to achieve superior maneuverability and range. The Zero fighter carried minimal armor protection specifically to reduce weight that would otherwise compromise performance. But this design philosophy assumed that combat damage would come from relatively low-energy projectiles like rifle-caliber machine gun rounds that Japanese pilots could potentially survive. American .50 caliber ammunition changed that calculation completely. The massive bullets possessed sufficient energy to penetrate any practical thickness of armor that aircraft could carry while maintaining flight performance. Even if Japanese designers added protective plating around engines, the .50 caliber rounds would punch through, creating the same catastrophic fragmentation that destroyed test engines at Yokosuka. The third and final test engine mounting proceeded with a modification that Yamada hoped might provide some defensive solution. His team had fabricated a 1/4-inch steel plate positioned 6 inches in front of the engine block, simulating armor protection that might be incorporated into future aircraft designs. The steel barrier represented approximately 50 pounds of additional weight, a significant burden for aircraft already operating at the margins of performance specifications. The .50 caliber round struck the steel plate at 2,800 feet per second, penetrated cleanly, tumbled through the 6-inch air gap, and slammed into the engine block with 90% of its original kinetic energy. The projectile's fragmentation pattern remained virtually unchanged. The crankshaft still sheared. Cylinder walls still cracked. The steel armor had proven almost completely ineffective while adding weight that would reduce aircraft range, climb rate, and maneuverability. Yamada dismissed his testing team and remained alone in the ballistics facility, studying the 3 destroyed engines that represented months of precision manufacturing and hundreds of man-hours of skilled labor. Each Nakajima Sakae engine cost the Empire approximately 30,000 yen to produce, required strategic materials from across the Pacific Empire, and incorporated the expertise of craftsmen who could not be rapidly replaced as casualties mounted. American ammunition was destroying these sophisticated machines with projectiles that cost approximately $1 each to manufacture. The economic mathematics of this exchange rate would prove as devastating as the ballistic performance itself. Japan was trading irreplaceable aircraft and trained pilots for American bullets produced by the millions in factories that operated beyond the range of Japanese military power. The evening sun slanted through the ballistics facility's high windows as Yamada began drafting his preliminary report. His engineering training demanded precision and honesty, even when delivering conclusions that undermined military optimism. The document would need to explain not just what American ammunition could do, but why Japanese industry could not develop effective countermeasures given current resource limitations and industrial capacity. 3,000 miles away, Gunnery Sergeant Morrison's B-17 completed its bombing run over Rabaul and turned for home. During the mission, Morrison had fired approximately 800 rounds from his ball turret, engaging 3 separate Japanese fighter attacks. The .50 caliber tracers had arced across the tropical sky like deadly meteors, and Morrison had observed 2 confirmed hits on a Zero that subsequently exploded in mid-air. He would never know that fragments of his ammunition were being analyzed in a Japanese laboratory, or that enemy engineers had concluded his weapons represented a technological advantage that could not be overcome through conventional defensive measures. The captured bullets sat on Yamada's workbench, cleaned of propellant residue and arranged in precise rows for photographic documentation. Each cartridge represented American industrial might, translated into a form that could be loaded into aircraft guns and fired at enemy targets. The copper jackets gleamed under laboratory lights, precision manufactured to tolerances that Japanese quality control could not consistently achieve in wartime production environments. If you find this story engaging, Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Lieutenant Nakamura returned to the laboratory carrying the metallurgical analysis results, a folder thick with spectrographic data and microscopic photographs of the bullet core's crystalline structure. The young officer's expression suggested the findings confirmed Yamada's worst suspicions about the technological gap between American and Japanese ammunition manufacturing. Yamada-san. The analysis is complete, Nakamura reported, spreading technical documents across the workbench beside the captured ammunition. The Americans are using a sophisticated alloy composition that we cannot duplicate with available materials. The steel core contains 4% nickel, 1.5% chromium, and 0.6% molybdenum, along with carefully controlled carbon content. This combination produces exceptional hardness while maintaining ductility that prevents brittle failure during high-velocity impact. Yamada studied the spectrographic data with growing appreciation for American metallurgical expertise. The alloy composition represented sophisticated understanding of how different elements affected steel properties under extreme stress conditions. Nickel enhanced toughness and impact resistance. Chromium improved hardness and corrosion resistance. Molybdenum, the critical element that Japan could not readily obtain, dramatically increased strength at elevated temperatures while maintaining ductility. The heat treatment process is equally sophisticated, Nakamura continued, pulling out a series of microscopic photographs showing the steel's grain structure. They are using a combination of austenitizing at approximately 900 degrees Celsius, followed by oil quenching and tempering at 400 degrees. This produces a martensitic structure with fine carbide precipitation that explains the exceptional hardness we observed. Our steel mills cannot achieve this level of metallurgical control in mass production. The technical explanation confirmed what Yamada had suspected from initial observation. American industry possessed capabilities that extended far beyond simple manufacturing volume. The .50 caliber ammunition represented systematic application of materials science, precision manufacturing, and quality control at scales that Japanese industry could not hope to match during wartime production conditions. What about the jacket design? Yamada asked, examining the copper sheathing under magnification. The controlled fragmentation pattern suggests deliberately engineered weak points rather than random failure. Nakamura nodded, producing additional photographs that showed the jacket's internal structure. The copper jacket varies in thickness from 0.03 inches at the tip to 0.05 inches at the base. This graduated thickness creates stress concentration points that initiate tearing in predictable patterns during impact. The jacket is not simply a protective covering, it is an integral component of the projectile's terminal ballistics design. The revelation demonstrated another level of American engineering sophistication. Japanese ammunition designers had traditionally treated bullet jackets as simple protective sheaths to prevent barrel fouling. The Americans had recognized that jacket design could be optimized to enhance terminal performance, turning a necessary component into an active contributor to projectile lethality. Yamada measured the jacket thickness variations with precision calipers, confirming Nakamura's measurements to within 0.02 of an inch. The consistency across multiple sample cartridges suggested automated manufacturing processes that maintained extraordinary quality control despite producing millions of rounds monthly. Japanese ammunition production, dependent on skilled craftsmen making individual adjustments to compensate for material variations, could not achieve such uniformity even in small experimental batches. The implications extended beyond ammunition technology to fundamental questions about industrial philosophy. American factories had invested heavily in precision tooling and automated production systems that required enormous capital expenditure but generated consistent quality at massive scale. Japanese industry, constrained by limited capital and raw material shortages, relied on skilled labor to compensate for less sophisticated manufacturing equipment. The approach worked adequately for limited production runs, but collapsed under the demands of total war, where volume and consistency both mattered critically. Nakamura-san, prepare a comprehensive technical report documenting all findings. Yamada ordered, gathering the test data into organized folders. Include detailed photographs of the engine damage, complete metallurgical analysis, and honest assessment of our capability to develop countermeasures. Admiral Yamamoto needs accurate intelligence, not optimistic speculation that might inform flawed strategic decisions. The young lieutenant hesitated, understanding that his superior was effectively documenting Japanese technological inferiority in a report that would circulate among the highest levels of military command. Yamada-san, such candor might be interpreted as defeatism by officers less familiar with engineering realities. Yamada met his subordinate's eyes with the calm certainty of someone who valued professional integrity over political expedience. Our pilots are dying because aircraft designers lack accurate information about enemy capabilities. If my report offends some staff officer's sense of national pride, that is considerably less important than providing intelligence that might save Japanese lives. Prepare the documentation as I have instructed. At Mitsubishi Heavy Industries Nagoya Aircraft Plant, Chief Designer Jiro Horikoshi received Yamada's preliminary findings on September 2, 1943. Horikoshi had designed the Zero fighter that dominated Pacific skies for the war's first year, creating an aircraft of such elegance and performance that American pilots initially refused to believe Japanese engineers could produce such sophisticated machinery. But elegance meant nothing against ammunition that destroyed aircraft, engines with single hits. Horikoshi studied the technical diagrams showing 50 caliber projectile penetration through Sakae engine blocks, his designer's mind automatically calculating the engineering challenges of providing effective protection. The Zero's empty weight was just 3,970 pounds, achieved through systematic elimination of any component not absolutely essential for flight performance. Adding sufficient armor to protect against American ammunition would require at least 200 pounds of steel plating, reducing range by 18% and climb rate by 22%. The modified aircraft would lose the performance advantages that made the Zero effective in combat. It would turn more slowly than American fighters, climb less aggressively, and possess insufficient range for the extended missions that characterized Pacific naval operations. Attempting to armor against 50 caliber ammunition would create an aircraft inferior to enemy fighters in every measurable category, while still remaining vulnerable to the massive projectiles. Lieutenant Commander Saburo Sakai, Japan's most successful surviving fighter pilot with 64 confirmed victories, reviewed Yamada's report at Yokosuka Naval Air Station with the practical understanding of someone who had faced American 50 caliber fire repeatedly. Sakai had been shot down twice by B-17 gunners, surviving only through exceptional piloting skill and considerable luck. He understood viscerally what the engineering analysis explained mathematically. The Americans have learned to concentrate their fire, Sakai told a group of replacement pilots during a tactical briefing in late September. When you attack their bombers, you face not just one 50 caliber gun, but 6, 8, sometimes 10 guns, firing coordinated defensive patterns. If even a single round strikes your engine, the aircraft is finished. You have perhaps 30 seconds before complete. Power loss, forces, emergency landing, or bailout. The young pilots listened with the intense attention of students who understood their survival depended on lessons learned through others' combat experience. Most would be dead within 3 months, victims of the attrition mathematics that governed Pacific aerial warfare. Japanese pilot training, once the most rigorous in the world, had been shortened dramatically to replace mounting casualties. New pilots arrived at frontline units with barely 200 flight hours, facing American aviators with 5 times that experience and superior equipment. Avoid extended pursuit of damaged bombers, Sakai continued, his scarred face showing the accumulated trauma of 3 years in combat. The Americans understand that wounded aircraft make excellent bait. They allow crippled bombers to struggle behind their formations, knowing we will attack. Then their escort fighters dive from altitude and destroy us while we concentrate on the seemingly vulnerable target. Their 50 caliber ammunition gives them killing power at ranges where our 20mm cannons are ineffective. At Rabaul's battered airfield, Flight Petty Officer Hiroyoshi Nishizawa implemented Sakae's tactical advice during the daily battles that characterized the Solomon's air campaign. Nishizawa, who would eventually achieve 87 confirmed victories before his death in October 1944, had developed attack techniques specifically designed to minimize exposure to American defensive fire. His approach required diving from high altitude at maximum speed, firing a brief burst at the bomber's cockpit or wing root, then immediately breaking away without attempting to observe results. The tactic reduced his vulnerability to defensive guns but also decreased his effectiveness, as the hasty firing solution rarely achieved optimal shot placement. But survival meant accepting reduced efficiency in exchange for avoiding the 50 caliber streams that killed Japanese pilots with mechanical regularity. On November 5, 1943, Nishizawa led a flight of 6 Zeros against a formation of 12 B-25 Mitchell bombers, escorted by 16 P-38 Lightning fighters over Bougainville. The Japanese pilots achieved initial surprise, diving from 22,000 feet with the sun behind them. Nishizawa's opening burst struck a Mitchell's right engine, his 20mm cannon shells exploding against the cowling with visible effect. But before he could execute his planned breakaway, a B-25 tail gunner opened fire with twin 50 caliber machine guns from 400 yards range. The first burst missed, tracers arcing past Nishizawa's canopy close enough that he felt the pressure wave from their passage. The second burst struck his Zero's engine with 3 rounds that arrived within 17 milliseconds of each other. The first bullet penetrated the Sakae engine's crankcase at a shallow angle, its hardened steel core tumbling as predicted by Yamada's ballistic analysis. The projectile sheared through 2 cylinder walls before striking the crankshaft and fragmenting into 9 major pieces. The copper jacket peeled away in strips that sliced through oil galleries and coolant passages, creating secondary damage throughout the engine's internal structure. The second round struck the propeller reduction gearbox, destroying the bearings that allowed the propeller to rotate at reduced speed compared to the engine's crankshaft. Metal fragments from the shattered gears ricocheted through the accessory section, severing fuel lines and electrical connections in a cascade of failures that occurred faster than human reaction time could process. The third bullet punched completely through the engine block and exited through the firewall, missing Nishizawa's left knee by less than 4 inches before embedding itself in the instrument panel. The projectile's passage created a 1/4-inch hole that admitted a stream of superheated oil vapor and combustion gases directly into the cockpit. Nishizawa's Sakae engine seized completely within 8 seconds of the initial hits. The propeller, no longer driven by engine power, windmilled freely in the slipstream while oil pressure dropped to 0 and cylinder head temperature spiked beyond the instrument's measurement range. Black smoke began pouring from the shattered engine, cowling as lubricating oil ignited upon contact with red-hot metal surfaces. The Japanese pilot initiated emergency procedures with the automatic responses drilled by hundreds of hours in combat. Mixture control to idle cutoff, magneto switches off, fuel selector to off. The Zero, now a 17,000-pound glider at 14,000 feet altitude, began its inevitable descent toward the Solomon Sea's dark waters 40 miles below. Nishizawa calculated glide angles and wind drift with the precision of a navigator, trained in dead reckoning over featureless ocean. His aircraft was losing altitude at approximately 800 feet per minute. He had perhaps 17 minutes of controlled flight remaining before ditching became unavoidable. The nearest Japanese-held airfield lay at Buka, 63 miles northwest. The mathematics were unforgiving. He would fall 6,000 feet short of the runway, even with perfect navigation and optimal glide performance. Behind him, the air battle continued without pause for individual casualties. American P-38 fighters had engaged the remaining Japanese Zeros, turning the sky above Bougainville into a 3-dimensional chess game played at 400 miles per hour. The distinctive sound of 50 caliber gunfire echoed across the engagement area as American pilots implemented tactics specifically designed to exploit Zero vulnerabilities, documented in Eddie Sanders' captured aircraft. Analysis. Nishizawa nursed his crippled Zero toward the coastline, milking every foot of altitude from the graceful fighter's excellent glide ratio. At 4,000 feet, He could see breakers marking the reef line around Bougainville's southern tip. At 2,000 feet, he selected a stretch of beach that appeared free of obstacles and vegetation. At 500 feet, he began his final approach, extending landing gear despite knowing the soft sand would probably flip the aircraft onto its back. The Zero touched down at 95 miles per hour, its main wheels digging immediately into loose sand that grabbed at the tires like quicksand, seizing a drowning man. The fighter's nose dropped sharply as the tail came up, and for one suspended moment, Nishizawa thought the aircraft might actually survive intact. Then the propeller blades dug into sand, and the Zero flipped completely over, crushing the canopy and trapping Nishizawa upside down in the wreckage. He hung suspended by his harness straps, tasting blood from where his face had struck the gun sight during the impact. Aviation fuel was dripping from ruptured tanks, forming an expanding pool beneath the inverted cockpit. Nishizawa released his harness and dropped onto the collapsed canopy, cutting his hands on shattered glass as he scrambled clear of the wreckage seconds before it erupted into flames. The Zero burned with intense heat that drove Nishizawa back from the aircraft he had flown for 7 months and 23 combat missions. He watched 300,000 yen worth of precision manufacturing reduced to twisted metal and ash, destroyed ultimately by 3 American bullets that cost less than a single pilot's boot leather. The economic exchange rate, multiplied across thousands of similar encounters throughout the Pacific Theater, was grinding Japanese air power into statistical irrelevance. At Yokosuka Arsenal, Chief Engineer Yamada compiled his final report during the last week of November, 1943. The document ran to 47 pages, incorporating ballistic test data, metallurgical analysis, tactical assessments from experienced pilots, and strategic recommendations for Japanese aircraft design. The conclusions made for grim reading among military planners who still harbored illusions about achieving favorable outcomes through superior fighting spirit. American .50 caliber ammunition represented a technological advantage that Japanese industry could not counter through conventional defensive measures. Armor protection sufficient to defeat the massive projectiles would degrade aircraft performance to unacceptable levels. Self-sealing fuel tanks, while theoretically possible, required synthetic rubber compounds that Japan could not manufacture in adequate quantities. Engine protection systems added weight without providing reliable defense against bullets designed specifically to defeat such countermeasures. The report's final section addressed the fundamental strategic problem that transcended individual technical challenges. American industrial capacity was producing .50 caliber ammunition at rates approaching 3 million rounds daily across multiple manufacturing facilities. This production volume, sustained month after month, created an inexhaustible supply of projectiles that American forces could expend with minimal concern for conservation. Japanese pilots faced enemies who could afford to miss 9 shots out of 10 and still achieve devastating cumulative effects. Japanese ammunition production, constrained by material shortages and limited manufacturing capacity, could not sustain comparable expenditure rates. Zero pilots carried 60 rounds per 20mm cannon, sufficient for approximately 34 seconds of maximum rate fire. Once ammunition was exhausted, the fighter became defenseless. American pilots with 2,000 rounds of .50 caliber ammunition could engage multiple targets throughout extended missions without approaching ammunition exhaustion. Yamada's strategic recommendations acknowledged realities that many staff officers refused to accept. Japanese aviation could not win an attrition conflict against enemies possessing overwhelming industrial advantages. The empire's best hope lay in forcing decisive engagements under circumstances that minimized American material superiority, using superior pilot skill and tactical innovation to offset quantitative disadvantages. But such engagements were becoming increasingly rare as American forces learned to leverage their technological advantages systematically. The report concluded with a paragraph that Yamada knew might end his career, but which professional integrity demanded he include. The captured American ammunition represents not just superior metallurgy or manufacturing precision, but a fundamentally different approach to industrial warfare. American forces treat ammunition as an expendable resource to be employed in overwhelming quantities, confident that their industrial base can sustain any reasonable expenditure rate. Japan must treat each cartridge as a precious commodity to be conserved carefully. This philosophical difference, perhaps more than specific technical disparities, explains the shifting balance of aerial combat effectiveness throughout the Pacific theater. Admiral Yamamoto read Yamada's report during the first week of December 1943 in his office aboard the battleship Yamato. The admiral had personally ordered the ammunition analysis, understanding that accurate intelligence about enemy capabilities was essential for making sound strategic decisions. What he read confirmed his growing conviction that Japan had entered a war it could not win through conventional military means. The .50 caliber ammunition analysis joined other intelligence assessments, documenting American advantages in radar technology, naval construction capacity, aviation fuel production, and industrial output, across every category relevant to modern warfare. Each individual disparity might be manageable through tactical innovation or operational brilliance. The cumulative effect of dozens of such advantages, all favoring American forces, created strategic conditions where Japanese victory required either miraculous good fortune or catastrophic American blunders. Neither seemed likely to materialize. American forces were learning from early mistakes, implementing tactics based on captured equipment analysis, and leveraging industrial capacity that dwarfed Japanese manufacturing output by factors of 10 or 20 in critical categories. The mathematics of attrition warfare were grinding inexorably toward conclusions that courage and fighting spirit could not alter. In the skies above the Marshall Islands on January 4, 1944, Gunnery Sergeant Frank Morrison fired his final combat mission from the ball turret of a B-17 nicknamed Memphis Belle II. The bomber was part of a 100-aircraft raid against Japanese installations at Kwajalein Atoll, encountering fierce resistance from Zero fighters that had been repositioned to defend what remained of Japan's outer defensive perimeter. Morrison's twin .50 caliber machine guns cut through the tropical sky in glowing arcs of tracer fire, each burst expending ammunition that Japanese engineers had analyzed but could not effectively counter. During the engagement, he fired approximately 900 rounds, achieving hits on 3 different Japanese fighters. All 3 aircraft subsequently crashed or were abandoned by their pilots, victims of engine failures caused by projectiles Morrison would never see examined in distant laboratories. The raid marked Morrison's 35th and final combat mission. He would return to the United States in February, receive an honorable discharge, and spend the rest of his life running a hardware store in Ohio. He never knew that fragments of his ammunition had been studied by enemy engineers, who concluded that American industrial capacity had achieved technological superiority that could not be overcome through conventional defensive measures. At Mitsubishi's Nagoya plant, designer Jiro Horikoshi began work on the A-7M Reppu fighter that was intended to replace the Zero in frontline service. The new aircraft incorporated lessons learned from 3 years of combat, including limited armor protection and self-sealing fuel tanks that added 620 pounds to empty weight. But the Reppu arrived too late and in too few numbers to affect the war's outcome. Only 9 prototype aircraft were completed before Japan's surrender in August 1945. The American .50 caliber Browning machine gun would remain in military service for 7 decades after World War II, equipping aircraft, vehicles, and naval vessels through the Korean conflict, Vietnam, Desert Storm, and into the 21st century. The ammunition technology, perfected at Winchester's ballistics laboratory in the 1930s, proved so fundamentally sound that it required minimal modification despite revolutionary changes in military aviation. Chief Engineer Yamada survived the war, returning to civilian life and eventually accepting a position with Toyota Motor Corporation, where he applied his metallurgical expertise to automotive engineering. He never spoke publicly about his wartime research, though colleagues occasionally noticed him examining American-manufactured components with an expression suggesting professional respect mixed with painful memories. The 3 destroyed Nakajima Sakae engines remained in storage at Yokosuka Arsenal until November 1945, when American occupation forces catalogued Japanese military equipment for historical documentation. Navy technical intelligence officers photographed the engine blocks, noting the characteristic damage patterns that matched ballistic reports from their own testing programs. The engines were eventually scrapped, their aluminum recycled for peaceful purposes in a Japan rebuilding under American supervision. Lieutenant Hiroyoshi Nishizawa, who survived his November ditching off Bougainville, continued flying combat missions until October 26, 1944, when he was killed aboard a transport aircraft shot down by American fighters over Mindoro. His 87 confirmed victories made him one of Japan's highest-scoring aces, but individual skill could not overcome the cumulative effect of American technological and industrial advantages that manifested in everything from ammunition to radar to aviation fuel. The strategic implications of the 50-caliber ammunition analysis extended beyond the Pacific theater. American industrial capacity, once fully mobilized for war production, generated military equipment at scales that Axis powers could not hope to match. Germany faced similar disparities in tank production, aircraft manufacturing, and ammunition output. The Soviet Union, despite suffering catastrophic territorial losses in 1941 and 42, still outproduced German industry in most categories of war material by 1943. The Second World War ultimately demonstrated that modern industrial conflicts would be decided as much in factories as on battlefields. Superior tactics and soldier quality mattered significantly, but they could not compensate for 10-to-1 disadvantages in equipment production. Japan's military leadership had gambled that superior fighting spirit and tactical brilliance could overcome material disadvantages. American 50-caliber ammunition represented one small component of the industrial reality that proved this gamble catastrophically wrong. The bullets that Morrison fired from his ball turret, that Yamada analyzed in his laboratory, and that destroyed Nishizawa's engine over Bougainville were products of a specific approach to warfare that emphasized systematic application of industrial capacity. American forces did not need to outfight their enemies shot for shot. They merely needed to deliver 10 shots for every enemy round fired, accepting that lower individual accuracy could be compensated through overwhelming volume. This philosophy, applied consistently across every category of military equipment from ammunition to aircraft carriers, created material advantages that skill could not overcome. Japanese pilots might achieve higher kill ratios in individual engagements, but attrition mathematics favored forces that could replace losses faster than enemies could inflict them. By mid-1944, Japan was losing trained pilots at rates exceeding training capacity, while aircraft production fell behind combat losses. The captured 50-caliber rounds that arrived at Yokosuka Arsenal in August 1943 represented far more than simple ammunition samples. They embodied an entire industrial philosophy, a specific approach to warfare, and a level of manufacturing sophistication that Japan's wartime economy could not replicate. Chief Engineer Yamada understood these implications clearly, documenting them in reports that helped military planners comprehend the true nature of the conflict they faced. But understanding problems and solving them are entirely different challenges. Japan lacked the raw materials, manufacturing capacity, and time necessary to close the technological gap that American ammunition exemplified. Each month of continued conflict widened disparities as American industry increased production, while Japanese factories struggled under resource shortages and strategic bombing. The war's ultimate outcome was determined by these industrial realities, long before the final battles confirmed what economics had already decided. Gunnery Sergeant Morrison's 50-caliber bullets destroyed more than enemy aircraft engines. They represented the application of industrial warfare principles that would characterize military conflicts throughout the 20th century and beyond. The side that could produce more equipment, maintain consistent quality, and sustain higher expenditure rates would ultimately prevail regardless of tactical brilliance or individual courage displayed by its opponents. This was the brutal lesson encoded in every 50-caliber cartridge that American factories produced, that Morrison fired in combat, and that Yamada analyzed in his Yokosuka laboratory. It was a lesson Japan learned at catastrophic cost across 4 years of Pacific combat, measured in shattered engines, burning aircraft, and young pilots who fell into anonymous ocean graves far from home. The mathematics of industrial warfare proved as unforgiving as the ballistics of hardened steel projectiles traveling at 2,800 feet per second. Both told the same story, written in copper and aluminum, documented in technical reports and combat statistics. American industrial capacity, applied systematically to every category of military equipment, had created advantages that courage could not overcome and skill could not compensate for. Chief Engineer Yamada understood this truth in August 1943, when he examined the first destroyed Sakae engine and recognized damage patterns that Japanese industry could not prevent. The knowledge brought no satisfaction, only the cold certainty of an engineer who had calculated impossible problems and found no viable solutions within available resources and constraints. 350 caliber bullets, costing less than $3 combined, had destroyed an engine representing 3 months of skilled labor and strategic materials gathered from across an empire. That exchange rate, multiplied across thousands of daily combat engagements, would grind Japanese aviation into statistical irrelevance long before the atomic bombs fell on Hiroshima and Nagasaki in August 1945. The war that began with Japan's surprise attack on Pearl Harbor in December 1941 ended with unconditional surrender aboard the USS Missouri in Tokyo Bay, September 2, 1945. Among the many factors contributing to that outcome, American ammunition technology played a role that historians would later recognize as more significant than tactical decisions or individual battles. The 50 caliber Browning machine gun and its devastating projectiles represented industrial warfare at its most fundamental level, where superior manufacturing capacity translated directly into battlefield advantage that skill could not overcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.